Okay, so last time we talked about the Curry effect, and then but we didn't go through any math, and some of you might be very happy about it. Okay, and so all the math would be here today, and to be honest, it's actually fairly straightforward. Okay, so okay, so this is the equation for Curry effect. Last time I mentioned about it, and then it's a little bit different from what we usually see, right? The nonlinear polarization. In nonlinear polarization, we have epsilon, chi, then we have E. So you see the dimension for these two equations is actually different. For here, you're using intensity, okay, which is actually make a lot of sense because you can measure intensity in your lab. Most people don't measure the electrical field of the light in the lab. Okay, so there must be a conversion, okay, between these two, and this conversion actually comes from the conversion between the intensity and your electrical field. And previously in all of our lectures, we were kind of a little bit casual, about the parameters between these two. Okay, there's actually some coefficient in the front. We're fairly kind of careless because we don't really mind like a factor of 2 or a factor of 4. But now you kind of have to think about it because N2 is something you can measure. Chi3 is again something you can measure. Okay, so if you mess up with the coefficient, you will have some inconsistency. Okay, so before we start on showing how to calculate this, let's just briefly go through how we get the relation between intensity and the electrical field. Okay, and previously I think equation we use a lot is something like this. Okay, and then if you use power is just intensity times the area of your light. Okay, there might be a typo in my note. So, okay. So this equation actually depends on your definition of the electrical field. Okay, this coefficient one half can actually be 2 if you define your electrical field differently. Okay, and that will contribute a factor of 4 when you convert the nonlinear coefficient and the chi3. Okay, so now let's derive this equation. Okay, so we know that the energy of your EM field is integration of the energy density. Okay, the energy density is E squared plus okay. There's another way to do it by using using P equals, forgot the other one. Let's just ignore it. Okay. Let's use this method. Okay. And so the first thing you want to know is that on average, okay, this integration, the E field and the H, they're oscillating with time, right? You're having a cosine or sine, whatever phase you have. So on average, you can also dt. Okay, so in certain time, in certain volume, this is your energy, okay? And on average, because we know this is cosine square integrated over time, let's say for a relatively long period. So that what that would mean is that you're taking the average of cosine square, right? So that's another half, 1/2, okay? So this will give you 4 in the front, and then that's all. Okay. This one, we need to make a notation now. Okay. The maximum value. Okay. Your integration is cosine omega t, and in front of cosine omega, of course, is the maximum value of your e. Okay, and then you do this integration, you get 1/2 in the front. Okay. And then we also know that the energy between electrical field and magnetic field, they kind of convert to each other. So they are identical. Okay, so we simplify this part by having this. Okay, so if you Google what is the electrical field, what is the energy of the light, some people will just directly show you this. And then you might wonder, well, are they forgetting the magnetic energy in the magnetic wave? The fact is that you actually add in a factor of 1/2 here, and then you kind of take that factor away when you do this. Okay, so by the end you get this. And this one, if you assume, okay, your EM field is uniform in a certain area, let's say in a fiber, right? Okay, you can kind of just write it down as this. Max times the volume. Okay. So now you need to, and also epsilon r then goes into n squared. Okay. Okay, now you need to convert this energy, okay, this is energy, into power. Okay, power. So the definition of power is the energy in unit time, right? So what we can do is that we can say power equals to the energy unit time. Okay, in unit time. So this will be, let's say, let's do it this way. It's easier to understand. Okay, you have a light coming in. Okay, you know the spot, the size of the light spot. Okay, that's something you can absolutely measure in your experiment. And then you're hitting it, let's say, onto a photodetector. Okay, your photodetector is receiving this energy. Okay, so now the power you receive, the energy you receive equals to the energy density and am I forgetting a C here? No, okay, good. Okay, this is the energy density. And now what's the volume? The volume is first the area of your beam. Is A. And then the distance of light propagate in 1 second, right? So all this EM field is going to hit this detector in 1 second. So that's the volume of your light. Okay. And this will be 1 over no, okay. 1 second times the speed of light. Okay, right? That's the length of your volume. Okay, and that gives you half epsilon C N A okay, it gives you this equation. And then, of course, the intensity would be power divided by your area, and that's okay. So now let's see how we need to define the electrical field so that you can directly substitute your E into here, right? So previously, I think we do this. Okay, your polarization, and then we say you have E okay. So this one is actually, when you use this one, it's really different, okay, because the Emax has two parts, right? One is this, one is complex conjugate. And if this is 0, then the complex, well, if this coefficient is 1, then complex conjugate is also 1, right? So the max is 2E, right? So when you define your E in this way, you have to get your Emax first, and then plug in this Emax to here. Okay. So in this definition, I is 2 epsilon E C N E squared. Okay. In this definition is this. This is also the equation you will find in the book of nonlinear optics. Okay. And for this definition, okay, if you want this 1/2 here, then you would need, this is definition 1. Definition 2. Okay, you want it to be okay. If you define it in this way, you have the 1/2 here, then you can start to use this equation. Okay, and then the I is okay. So which one should we use, right, in your own calculation? It really depends on your personal taste. Okay, and I personally prefer this one. Okay, why? Because think about it. In nonlinear optics, what we need to calculate, let's say E to the third. Then by this definition, you actually have this coefficient in the front, right? Half and then to a third, you get 1/8. Okay, and then it's very easy to forget about it. And then later, when you really expand this, you'll start to see there's coefficient of like this. Okay, and just overly complicated. And all this coefficient would not be, well, you're not saving yourself any trouble unless you start to use this, right? You start to use this, and then you say, I'm absolutely sure my definition is the same as everyone else, right? Yes. So in most cases, I would actually prefer this one, okay, because the coefficient is much more simpler, and then in many of the calculation, you don't have to do the last step. Okay, you don't need to do this actually in a lot of problems. And sorry, this one. And even if you do, you just remind yourself the coefficient is different. Okay. Okay. Now let's take a look of how the third order nonlinear effect can connect to the Curry effect. Okay. Okay, let's say you have a light and coming into a waveguide. Now this is something kind of interesting is for the Curry effect is that let's say you have, which notation I use? U1, okay. Okay, let's say you input the E1 at the frequency of I omega omega 1. Okay, the thing that we need to be a little bit careful about is that it doesn't necessarily mean your output is also just one frequency. Okay, and even, well, one obvious thing is that you have third harmonic generation, right? But that one requires phase matching, so it rarely happen. But even without even exclude the third harmonic generation, this thing, especially if you put it in a resonator, like a cavity, okay, a single frequency input can actually generate hundreds of frequency output. So if you're working in a lab, I would say, do the experiment first, and then come back to work on the theory, okay? Because you might work on the multiple frequency theory, but then in the end, your experiment show only one frequency. Then you waste a lot of your time, okay? So the way we are going to approach here in this class is that we start from the simplest one. Let's say we have one input, and we also have one output. Okay, it's the ideal case. And for this one, what we do is we do this a lot of times, right? So, okay. Okay, we neglect that the tensor nature of this nonlinear coefficient. Okay, just for simplicity, now we expand this. Okay, and here you have E epsilon chi 3 times to the third. And so let's just do this expansion, okay? The first one you will have is you can actually split it into steps, okay? Right, this is a square of this, and then you do it again. Okay. do this, and then this one times this one. This one times this one. Then this one times this one. And finally the last one. And you can combine them. Okay, first one is that this one is a third harmonic generation, right? This one will give you e minus 3I omega t. Okay, and this is its conjugate, right? These two. The third harmonic generation, just like second harmonic generation, require phase matching condition, and the math is actually the same, so we're not really interested in this. Third harmonic generation, well, wasn't that much of a big deal in the past, but then it actually started to change by a kind of a little bit accident in a microresonator. So like 10 years ago, there's a postdoc in my advisors group. He used to be, well, he then went to Michigan as a professor. So what they do is that they have a resonator, okay, made of silica, and this resonator is really small. Okay, it's like 20 microns in diameter, and then made of glass. Okay, and the quality factor is really high. The photon lifetime is about 100 nanoseconds. Okay, so you can accumulate a lot of power inside this resonator. So the accident is that what they want to do at first is that they got this really big EDFA, and then they want to see how much power they need to input, via fiber input into the resonator to melt the glass, okay, to melt the entire resonator. Okay, there might be you might wonder why. Why do you want to do that? First is to test the breakdown point of your device. The second thing is that melting the glass could be quite useful, because after it becomes liquefied, then you will start to have surface tension on your device. The surface tension tends to smooth out, right, your surface. So potentially you can change, you can convert a device with rough surface into a device with very smooth surface. So okay, so there's some kind of there's some motivation for them to do that. Okay, but I think the most case, well, the real thing is that it's just interesting, right, to see what will happen. And what they see is that it starts from 1550 nanometer, and they actually see the resonator looks like a green thing. It's emitting green light. Okay, you can see it by naked eye. And interestingly is that our naked eye is actually more sensitive to the green than most of the photo detector. Okay, so you first see it, then your detector see it. Okay, and so what happened is that there's a third harmonic generation inside the resonator, and they saw a pretty strong green light, and then they end up publishing in Nature Physics. Okay, quite amazing. And at first, this one doesn't draw much attention, but later, in recent years, now people are doing frequency combs with these resonators. And then one difficulty is that when you're going into visible wavelength, the dispersion of your device is difficult to control because there's a very strong material dispersion there. So it turns out to be hard to generate frequency comb here. So people generate frequency comb at this wavelength and then use third harmonic generation to convert it into green light. And why you want to have visible? Well, there's several reasons. One is that you, for example, if you want to use the frequency comb to calibrate the telescope, then most of the stars we're interested in emit visible light. So you kind of need to overlap the wavelength. Okay. And there are a few papers on this now, and actually I'm helping a group in China. They have an experiment, and then we're writing a paper together on this using frequency comb and convert it into third harmonic, or into green light third harmonic generation. And it's fun for that experiment because they can actually see violet. They can see a blue light, and then they can see I think light all the way down to 400 nanometers. Okay, so that's one thing. And then if you neglect this two, and then now you're left with this one, okay, this two. And this is just the complex conjugate of this one. Right. Chi3, and then have a factor of 3 here. Okay. Now, so this one looks pretty much like here. Okay. I requires E squared, right? And then to convert it into refraction index, we know the polarization that contains both linear and nonlinear. Okay, and then you would have epsilon chi1 plus 3 chi3 E squared E and then CC. Okay, the linear part is just chi. Okay. And then we do this a lot of time in this class. Okay, equals to 1 plus this thing. Okay. One plus chi1. Okay, 1 plus 3 chi3. Okay, you take the square root, you take out this term. Okay, why we take out this term? This one is just a refractive index, right? So we can say n naught. You have 1 plus. Now this is interesting. Usually, we already showed that how small n2 is in the last lecture. Okay, so this term is actually much smaller than 1. Okay, so you can take approximation here. This comes down to here. You have 2. Okay, this one is n knob square, 3 chi3. Okay, this is what you get. The refraction index is n of plus 2/3 chi3 n of. Okay. And now we need to make the conversion between E and I, right? And the E, our definition is like this. We don't have the 1/2 factor, okay? So I is 2 epsilon C, right? Okay, this is a part that we should be careful about. And you plug this in. Okay. So n one-third. Okay. And epsilon naught C. Okay. I think there's a square. Okay. So this is your N2. Okay. And for some reason, if you look up in the book, I think this chi2 for chi3 for some reason they don't agree on this, okay, with this equation. One possibility is that it could be just the measurement for N2. It's actually quite difficult, right, because it's very, very small. So for example, like for silica, the glass, there are various sources of N2. Okay, sometimes people write it down at 2.6, 10 to the minus 20. I think my group, we use 2.2, 10 to the minus 20. The fact is that none of us have measured it. We're just quoting numbers from the paper. And then you will actually be surprised if the error is less than 10%. It's actually pretty huge. And for some materials, there's no number exists because nobody ever measured it. Okay, and yeah, so keep that in mind. Okay, so this is the simplest case. This one is also called self-phase modulation. Okay, Curry effect in this form is also called self-phase modulation. The reason is your Z, right? This is your phase when you propagate the light, and this one is I 2 pi n lambda Z, right? So if your refraction index changed because of your own power, okay, your own electrical field, then you're causing a phase modulation, okay, based on your own electrical field. So that's called self-phase modulation. And now let's come back to this picture, and then we'll make things a little bit complicated. Okay, the next one is okay, the next one is 2 input. Okay, 2 input, not sure how many output. Okay. Well, the actual answer is almost infinite number of frequencies. Okay, so again, one good thing about nonlinear optics is that the math is actually, you can say it's a little bit tedious, but the good thing is it's simple. Okay, so you get E epsilon chi3. Okay, and then you have E1 plus E2 plus E1 star plus E2 star to the third. Okay, and if you kind of try to expand it, okay, it will be a little bit terrifying. Okay, so I strongly advise you not to do it. Okay, you guys have Mathematica now, right? You don't have to do this stupid thing. Okay, it's really stupid if you try to calculate this, just wasting your life. Okay, and we can use in another way, like you can use multinomial. Okay. Okay. Well, this equation is very useful to you because you can work with nth order of nonlinear effect, right? With m number of input, so it's kind of universal. Okay. But then the thing that kind of hurts a little bit is that I think if you do try to ask your computer to calculate the numerical value, okay, this term, I think the computation complexity, I think it's always go like this. Okay, if you do a numerical calculation, maybe wrong, maybe this, one of them. Okay, so what will happen is if you do this term and then you try to calculate the dynamic of your system using this, and then your computer will kind of explode. Okay, and actually I tried this like a few years ago when I first went to grad school, and then I think my computer stopped responding once I increase the number to this one is 1,000, this one is 3. Okay, and it kind of freeze. The thing is that it will eat up your RAM for some reason. It's a little weird. No, it's actually not weird. Yeah, when you do this mod. Okay, and there's actually a clever way to do it. Is this thing you can use Fourier transform to calculate. And we're not going to cover it, but there's a lot of papers on that. Okay, and this one equals to, first you need to, let's say, select, right, the number of k1, k2, x, and km, right? And then k1 plus k2 plus km all the way down equals n, right? It's a very basic thing. And then you have n, k1, k2, km. Okay, very simple. Okay. And the coefficient is always the integer. Okay. Now, so let's look at our equation here. We just take out this term. Okay, we don't care that much about this coefficient for now. So we have x1, x2, x3, x4. We have 4 of them, and we're only interested in the case where phase matching condition doesn't play a role, right? If you have E2 third, then you need to care about the phase matching condition. Okay, so that would mean we want our end result, let's say, say if omega 1 minus omega 2 much smaller than omega 1. Okay, this is our first assumption. So the frequency difference between omega 1 and omega 2 is much smaller than your original frequency of light. And in real experiment, this can be, usually this can be like within a terahertz. Okay? You can tune 2 of your lasers, okay, to do that. And this one is usually roughly around 200 terahertz. Okay, so satisfy this condition. Okay, and then the next thing is that the output, right? The output. If you want your output frequency, say question mark omega, is close to omega 1 and omega 2, right? Then this term cannot exist. Also this term. Okay, these are third harmonic generation. Okay, it doesn't match what we want. Okay, so from this you start to see that you need at least one conjugate or two conjugate, right? Because the conjugate will flip, right, the sign here. When you multiply these two, they canceled, right? So to get an output which frequency is close to omega 1 and 2, you need at least one conjugate or you need two conjugate. Okay, two conjugate, you still multiply with this one. Okay. So this one we can get a few combinations. Okay, the way to count it is we can only take one or two of E1, right? If it, right, this one doesn't work. Okay, so you first get E1. Let's start from the highest order, E1 square, right? And then E1 square. Now you can't pick up E2 because the frequency will be high. It will be omega 1 plus omega 1 plus omega 2, right? That's a different frequency. Okay, so you can pick up E1 star or E2 star. Okay. Okay, so that's the first two terms. And then E1, okay, the first, just E1, okay. For this one, well, then this is a little bit tricky here, okay. First of all, you can't pick up E2 square, right? For the same reason, if you pick up E2 square, the frequency will be omega 1 plus 2 omega 2, right? That's a very high frequency. Okay, so you can pick up E2, but only one of them, okay? And then you can pick up E1 star, or you can do E1, E2, E2 star, right? Okay. And the other way is you don't pick up E2, right? You have E1, this one, E1 star square. Okay, this is one option. And then continue E1. If you only pick up one E1 conjugate, then naturally you need a E2 conjugate, right? And then there's the final one is that if you don't pick up E2 null E1 conjugate, then you get E1 E2 conjugate square. Okay, that's already all the combination you will have by having a E1 in your polynomial. Okay. Well, at first you might think, wow, this is terrible because we've only done one of it. And then it's already a lot of terms. But the fact is that there's only one more to do. Okay. When you're done, so right now we have list all the terms that contain E1. Okay. Now the second one would be the terms without E1, but with E2. Okay. So we have, I think, yeah, we should be able to finish with this. E2. Again, first we have E2 star. E2 square. Okay, and then they can pair with E1. Also pair with E2 star. Okay. And then you can pick only one E2. Okay. And you can get E1 star square. And then if you only pick up one E1, then you have to pick up a E2 star. Okay. And finally, if you don't pick up E1 star, then you will have E2. Okay. And do we need to calculate this one? Now we've done this two. Do we have to do this one? No, right? Because you need a E and a conjugate to make the output frequency close to your input, right? So these two terms we don't need to calculate it. Takes a little longer than I thought, but now let's put in the coefficient. Okay, this will be fun. And any idea? Do we need to go through every one of them? Okay. There's actually only two types of terms here. One is that all three terms are different, right? The other term is the other type is that there are two terms that are identical, right? So there's only two types of coefficient here. Let's do the simple one first. This one. Three are all different. Of course, this one is always 6, right? 3, and then 1, 1, 1, right? Simple. 6, 6, 6. 6. Okay. And then for this, you have 1 and 2. Okay. So all the rest you have 3. Okay. So this is actually pretty nice. It's complicated in some way, but it's manageable. Okay. Now let's kind of put them in different class, I would say. Okay. Each of them represent a different physics process. Okay. So the first type, I think we can write it down here. Okay. So the first type is, of course, we want to put in the things we know first, right? We know self-phase modulation. This is self-phase modulation, right? U1 is the amplitude of U1 squared and times U1, okay? Self-phase modulation. And what else? This is complex conjugate of the self-phase modulation. And then this is self-phase modulation of E2, right? And then this is a complex conjugate of self-phase modulation of E2. Okay, so probably we still need this. Okay, so the first term we have here is okay. It's self-phase modulation. We already get the 3 in the front. Okay. U1. Okay, this is self-phase modulation. Self-phase modulation. The second term that's kind of also interesting is that we want to collect the terms that their frequency have not changed. It's still omega 1 and omega 2, right? Because then we don't need to include new frequencies. That's, again, very simple for us to calculate. Okay, so for those purposes, we can see here U1 conjugate E2. This one has a frequency of E2, right? And then this one has a frequency of U1. Same here. This is a complex conjugate of this. And then this is a complex conjugate of this. So second term is actually, there's a factor of 2 here. 2 U2 squared U1 2. So these two actually looks pretty similar. Okay, they form U1. But this one is the intensity of the light itself modulate the refraction index. This one is the intensity of another laser, another light, modulate your refraction index. Right? So this is called self-phase modulation, and this is called cross-phase modulation. Okay, cross-phase modulation. And the important thing is cross-phase modulation is 2 times larger than self-phase modulation. And this actually becomes important if you have 2 input, and then you need to determine what's the refraction index change in your system. Okay. And let's go on the third one. And this type of terms start to create new frequencies, right? You see it's 2 omega 1 minus omega 2. Okay, so there's 1, 2, 3. There should be 4 of them. 4, yes. 4 of them here. Okay, let's write it down. This is its conjugate. And this term actually also has a name. We need to explain a little bit of this and then to give you a name. Otherwise, it sounds weird. Okay. So this one, let's write it down. This is omega. Okay. So you have omega 1, omega 2. These are the two input lasers you have. This term is 2 omega 1 minus omega 2. Okay. Omega 1 plus omega 1 minus omega 2. Right? So you see it's omega 1 plus the difference between them. Or if you want to write it a little bit better, because right now we are saying omega 2 is larger than omega 1, so you can put it in this form. Minus omega 2 minus omega 1. Okay. So the frequency at omega 1 minus the difference. Right? They are equal distance here. So this belongs to the first term. The second term here, you have omega 2 minus omega 1. Right? And this one, you get omega 2 plus omega 2 minus omega 1. So it means you start from omega 2, and then you plus the frequency difference. You add the frequency difference. Okay? So it's here. Okay. So by having two input, you actually create another 2, and the frequency difference is the same. Okay. And because it actually has 4 waves here, this term called 4-wave mixing. Okay, it's called 4-wave mixing. And the interesting thing is that, well, we say when we calculate the nonlinear polarization, you need to include all the field, right? All the electrical field. So now you have, probably we can call it, this is omega 3. This is omega 4, right? If you include those, come E1, E2, E3, to the third. Okay. What you find is that there will be again 4 mixing terms. But let's say these two mix, it will generate you another one. This two mix, it will generate you another one. Okay. And then now you have to include these two, right? And this mix give you this one. Okay. So this process, if you start to include all the terms in the 4x mixing, this process just continue and continue. And this is called cascaded 4-way mixing. Okay. We'll spend another 5 minutes to finish this. Okay. So you might think, wow, this is so great, right? Starting from 2 lasers, you can convert it to infinite number of lasers. If only life is that simple, right? So now let's look at the condition, okay? When this process will stop. Let's take omega 3 as an example. Okay, if you have omega 3 in the nonlinear equation, you get this. Okay. Okay, there's a momentum term here, and this is the same for actually all the other mixing terms. Always showed up like this, or you can even show it up as, so you can have EI, EJ, EK. Okay, then this term would be I, KI, KJ, K. Why would I have KK here? Yeah. Okay. So it actually makes sense now because the Fourier mixing in the quantum picture is that you have two input, I and J, and then you generate two waves, K and L. Okay. In this case, two of the input are at the same frequency. So in this process, you want frequency to conserve. That's the energy conservation. And also you want momentum conservation, right? K input equals to K output. Okay. And let's write it down, okay? Let's still go back to here. Let's use this. Okay. We would have K1, K2, K3 equals to 2 pi lambda and then 2n1 minus n2 minus n3. Okay. Omega 1, omega 2, omega 3. And previously we know that from your midterm, you know that you can have omega here. Okay. This is your refraction index. Okay. Usually it will look like this. Okay. So when the frequencies are fairly close, the first order is always linear, right? Or any lines, okay? So to the first order, they actually always phase match. Okay? If you do a linear expansion, for example, you can do n delta omega equals n at omega 1, right? Plus dn d omega times delta omega. Okay, if you only use this, then this term is 0. It's always phase match. But unfortunately, there's other terms, right? You have higher order terms here. A half d square n d omega square, and then delta omega square. Okay. So when you start to cascade a lot of them, then this you need to start to consider the higher order dispersion. Okay, it's not linear anymore. Okay, and this is called group velocity dispersion. And group velocity dispersion is the thing that limit the how far you can go with the cascaded Fourier mixing. Okay, and then in our lab, we don't use waveguide. We use resonator. We can get roughly about 500 lines. Okay, and then if we use highly nonlinear fiber to further boost this process, we get 5 times. We actually get 5,000 lines. Okay, and then I know some labs, like in NIST, because their line spacing is very small. Okay, they can actually get more than 100,000 lines. Okay, and so this is something very active currently in the research. Okay, and that's all for today. Okay.